Something massive, far beyond anything humanity has ever recorded, has just appeared on the farthest edges of the known universe. Not a star, not a galaxy, not even a supercluster. This structure is bigger and more mysterious. It was uncovered in a dark matter map, a chart of the invisible universe. What scientists found has no parallel. It doesn't fit into any current model of cosmology. It's so vast that it dwarfs known structures like the Sloan Great Wall or the Hercules Corona Borealis Great Wall. And yet, it wasn't seen with the naked eye. It was found through gravitational distortion, something powerful enough to warp the fabric of space. This isn't science fiction. This is raw data coming from the newest generation of instruments, using gravitational lensing and deep space surveys to reveal what light alone can't show us. The discovery suggests that something enormous, possibly hundreds of millions of light years across, exists beyond the cosmic horizon. But that raises a terrifying question. If it's beyond the observable universe, how are we even detecting it? Could it be part of a larger, unseen reality? Or are we witnessing the remnants of something ancient, something left behind when our universe was still young? Scientists are baffled. Cosmologists are split. Theories are flying in from every direction. And while many researchers are calling for caution, even the most skeptical minds admit they've never seen anything like this. This isn't just a wrinkle in our map of the cosmos. It's a tear in the narrative we thought we understood. A disruption in the limits of the known universe. And as telescopes refocus and data streams in, one thing is becoming alarmingly clear: we may have just discovered something that was never supposed to be found. For centuries, humanity believed the stars we could see formed the boundary of the universe. Then came Galileo, Newton, and eventually Hubble, each widening our cosmic perspective. Today, the observable universe spans an estimated 93 billion light-years in diameter. That number alone is staggering, but it's crucial to remember it only accounts for what we can see. Beyond that, the story becomes less certain, and much more mysterious. The observable universe is not the entirety of existence. It's merely the region from which light has had time to reach us since the Big Bang, about 13.8 billion years ago. Light takes time to travel, and because the universe is expanding, we can see objects that are currently much farther than 13.8 billion light-years away. This strange paradox happens because space itself is stretching. The result is a visible bubble of 93 billion light-years, with Earth roughly in the center, not because we're special, but because the observable universe is defined from our point of view. However, this bubble isn't a wall. There's no cosmic border out there. Just a limit to what our instruments, and the laws of physics, allow us to detect. This is known as the cosmic horizon. It marks the edge of the observable, not the actual. And that's where things get interesting. We rely on light, photons, to map the universe. But the universe is mostly made of things we can't see. Dark matter, which doesn't emit or absorb light, makes up 27% of the universe. Dark energy accounts for another 68%. Ordinary matter, everything we can see, touch, and measure, represents less than 5% of what's really out there. That means the vast majority of our universe is invisible to us. We navigate it indirectly, like reading shadows on a wall and trying to guess the shapes behind them. This is where the concept of beyond moves from science fiction into scientific theory. Because if we can detect gravitational forces or distortions originating from regions past our observational reach, then those regions, whatever they contain, must exist in some form. It's no longer just theoretical. The discovery of a giant structure beyond the observable universe forces us to ask uncomfortable questions. Is the universe truly infinite, or does it have layers and borders that we've yet to understand? Are there other regions of space, filled with matter, energy, and perhaps even life, that lie just beyond our observational capabilities? Cosmologists have long suspected that the universe we know is just a fragment of a much larger whole. Some models suggest an infinite expanse. Others hint at a multiverse, where countless other universes may exist, each with different laws of physics. Until now, these ideas were mostly speculative. But when something beyond the edge leaves a fingerprint, when a structure large enough to distort the cosmic web appears in our data, the line between theory and evidence begins to blur. What was once confined to imagination is now surfacing in scientific journals and deep sky data. The cosmos may be vaster, more complex, and infinitely stranger than we ever imagined. And with each discovery, the boundary of the known universe shifts, not just outward, but deeper into the unknown. Dark matter is one of the most perplexing mysteries in modern science. It neither emits light nor interacts with electromagnetic radiation, which means we can't observe it with traditional telescopes. And yet, we know it exists. Not because we've seen it, but because we've seen what it does. It tugs at galaxies, bends light, and shapes the very structure of the universe. According to current models, dark matter makes up roughly 27% of the universe, far outweighing ordinary matter, the stuff that makes up stars, planets, and people. Despite its invisibility, it plays a crucial role in holding galaxies together and forming the cosmic web that stretches across space. The challenge is that we are attempting to chart an entity that doesn't glow, reflect, or radiate. It's like trying to map the wind by watching the trees. We know dark matter is there because of its gravitational influence. Galaxies rotate faster than they should if they only contained visible matter. Light from distant objects bends unnaturally as it passes through seemingly empty regions of space. These gravitational anomalies are the fingerprints of dark matter. To understand how scientists map the invisible, we need to explore the techniques that allow us to sense dark matter's presence. One of the most powerful methods is gravitational lensing. This is a phenomenon predicted by Einstein's theory of general relativity, where the gravity of a massive object bends and distorts the light of objects behind it. When we observe light from a galaxy that appears warped or magnified, we can calculate the mass of the invisible structure doing the bending. These distortions, when observed across vast regions of the sky, become clues that help cosmologists construct maps of dark matter distribution. Another method involves tracking the movement of galaxies. When astronomers observe clusters of galaxies moving at unexpected speeds or see galaxies staying bound together despite lacking enough visible matter to account for their cohesion, they infer the presence of dark matter. It's like watching dancers on a stage move in ways that only make sense if an invisible partner is guiding them. The pursuit of dark matter mapping has gained momentum with the deployment of advanced tools designed for deep space exploration. One of the most significant recent developments is the launch of the European Space Agency's Euclid telescope. Euclid is built specifically to explore dark matter and dark energy by capturing the shapes and positions of billions of galaxies. Over the course of its mission, Euclid will map a third of the sky with unprecedented resolution, offering new insights into how dark matter is distributed across cosmic time. On the ground, the Vera C. Rubin Observatory in Chile is poised to transform our understanding of the dark universe. Its Legacy Survey of Space and Time, or LSST, is expected to create a 3D map of the sky using repeated imaging over a 10-year period. With its 3.2 gigapixel camera, the largest ever built for astronomy, the Rubin Observatory will monitor changes in the brightness and movement of celestial objects, revealing how dark matter influences their behavior. Then there's the James Webb Space Telescope, a marvel of infrared observation. While Webb wasn't designed specifically for dark matter, its ability to peer into the earliest epochs of the universe provides vital context. By examining the formation of the first galaxies and the patterns of their growth, Webb helps scientists model the role of dark matter in galactic evolution. When combined with dark matter maps, its data adds layers of depth, helping refine our understanding of how the universe assembled itself. Beyond telescopes, another crucial source of information comes from the cosmic microwave background, the afterglow of the Big Bang. Instruments like the Planck satellite have measured minute fluctuations in this ancient light. These fluctuations tell a story about the early distribution of matter and energy in the universe. When scientists analyze these patterns, they find that only a small portion of the energy corresponds to visible matter. The rest, unaccounted for by what we can see, points directly to dark matter and dark energy. By merging data from gravitational lensing, galaxy velocities, early universe radiation, and deep field imaging, cosmologists create detailed maps of dark matter. These maps don't show individual particles or objects. Instead, they reveal patterns, filaments, voids, and clusters, where dark matter is most densely concentrated. These patterns form the backbone of the universe, an invisible web upon which galaxies are strung like beads. As these maps grow in resolution and scale, something extraordinary has started to emerge. In recent surveys, scientists noticed distortions and gravitational effects that could not be explained by known structures. The magnitude and symmetry of these distortions hinted at something massive lurking beyond the edges of the observable universe. This is how the giant cosmic structure was first suspected, not from light, but from its gravitational fingerprint. It was as though a hand reached across the cosmic curtain and left an imprint on our side. What began as a theoretical exercise has evolved into a frontier of active discovery. The hunt for dark matter has transformed into a journey toward the edge of existence. And now, that journey may have uncovered something larger, older, and more mysterious than anyone ever imagined. The discovery that changed everything, an unexpected signal in the darkness. It started with a routine analysis. A team of astrophysicists was reviewing gravitational lensing data collected from overlapping dark matter surveys. The datasets came from several sources, including Euclid's early field maps and preliminary imaging from the Vera-Rubin Observatory. The researchers weren't looking for anything out of the ordinary. Their goal was to refine existing dark matter models and check for alignment with previous data collected by the Planck satellite and the South Pole telescope. But what they found was so out of place, so anomalous, that the project changed direction entirely. Buried deep in the farthest observable zone of the southern celestial hemisphere, just past the Eridanus constellation, the data showed something strange, a distortion that didn't match any known galaxy cluster, supercluster, or void. The gravitational lensing patterns were too strong, too coordinated, and spanned too vast a region to be a fluke or an error in measurement. At first, the assumption was instrument misalignment or statistical noise. That's always the safe bet in cosmology when something doesn't fit. But follow-up scans confirmed the anomaly. And when the team cross-checked the data with galaxy motion surveys and the subtle microwave background shifts from Planck, the evidence became undeniable. There was something there. Something enormous. The size of the structure couldn't be determined immediately. It didn't radiate light, so it had no defined edges. But by analyzing the extent of the gravitational lensing and the impact it had on background galaxies, scientists began to estimate its scale. Early models suggested it stretched over 1.4 billion light-years across, a span larger than the Sloan Great Wall, which held the previous record for one of the largest known structures in the universe. If verified, this structure would be not just larger but positioned far beyond where we thought such structures could exist. The implications were staggering. According to the standard model of cosmology, the universe should be homogeneous and isotropic at large scales. That means, statistically, matter should be evenly distributed in every direction once you zoom out far enough. Discovering a structure of this magnitude, especially one this deep in space and potentially outside our observable limits, threatened to challenge one of the core assumptions about how the universe evolved after the Big Bang. The reaction among scientists was a mix of disbelief and cautious excitement. At first, the results were submitted for internal peer review. Cosmologists from independent institutions were invited to audit the findings. They reanalyzed the raw data, adjusted for bias, checked for data contamination, and ran simulations. Each time, the anomaly held up. More surprisingly, once the community knew what to look for, faint hints of this structure were found in older, overlooked datasets from WMAP and even as far back as COBE. The evidence had been hiding in plain sight, too subtle to notice before but too consistent to ignore once revealed. The location of the structure is now the subject of intense focus. While exact coordinates vary depending on the reference system, the gravitational signature is concentrated near galactic coordinates roughly centered at 280 degrees longitude and minus 60 degrees latitude. That places it in one of the most understudied and dark corners of the southern sky. The region is partially obscured by galactic dust, which might explain why optical telescopes had missed it. But gravitational data doesn't lie, and it doesn't need light to make its case. In deep sky context, the structure lies well beyond the Laniakea supercluster, far past the Shapley concentration, and outside the range of even the Hercules Corona Borealis Great Wall. It sits beyond known cosmic filaments, suggesting that it may not be part of our current cosmic web at all. Some astrophysicists now speculate that it could belong to a deeper, more ancient structure, perhaps a remnant from a time when the rules of the universe were different, or even evidence of interaction with regions outside our observable cosmos. The discovery is still fresh, and the scientific community is in the early stages of understanding what this structure means. But one thing is already clear: this isn't a minor anomaly. It's a landmark finding. A shift in our understanding. A moment when the map of the universe expanded, not by inches, but by light years. We often say the universe is vast and mysterious. But now, with this new detection, it feels like that phrase doesn't even come close. Something massive is out there, massive enough to distort light, tug at galaxies, and bend our understanding of space. We've never seen it. We may never see it with light. But it's there, and it's real. And it just changed everything. What exactly is this gigantic structure? A shape without edges and a name without precedent. Once the initial shock of the discovery settled and confirmation came in from multiple observatories, scientists were left with the next impossible task: trying to define what, exactly, this gigantic structure might be. Its scale defies conventional categorization. It doesn't behave like a galaxy cluster. It doesn't fit within the known geometry of a cosmic wall. And yet, it appears too organized to be a random fluctuation in dark matter. The structure reveals a level of mass concentration and gravitational impact that suggests form and purpose, but lacks any visual signature. It exists solely through inference, in gravitational fingerprints and warped starlight. It has no glow, no heat, and no definable perimeter. So what are we actually looking at? The first logical hypothesis was that this could be a previously undetected supercluster. Superclusters are vast assemblies of galaxies bound loosely by gravity, like the Virgo supercluster to which our own Milky Way belongs. These formations are among the largest recognized structures in the universe. They stretch for hundreds of millions of light-years and often contain smaller galaxy clusters and filaments. But this new structure doesn't just stretch, it swallows. Based on gravitational lensing models, the span of this anomaly reaches well over 1 billion light-years. That's far too large to be considered a standard supercluster. And it lacks the luminous mass one would expect in such a grouping. No trail of galaxies. No visible hot gas. Nothing but gravitational warping so powerful it bends background light on scales never observed before. Next came the idea of a cosmic wall. These are even more immense than superclusters, forming part of the filamentary skeleton of the universe. Cosmic walls are enormous sheets of matter, arranged between great voids of near-empty space. The most famous example is the Sloan Great Wall, which spans roughly 1.38 billion light-years and was discovered in 2003. At the time, its discovery caused major debate, since its size appeared to violate the cosmological principle, the idea that the universe, at a sufficiently large scale, should look roughly the same in every direction. But the Sloan Wall eventually became an accepted anomaly. Then, in 2013, a new record was set by the Hercules Corona Borealis Great Wall, an enormous gamma-ray burst cluster spanning over 10 billion light-years in length. It became the largest known structure ever identified, casting further doubt on the limits of homogeneity. The structure discovered now, however, doesn't simply rival these titans. It emerges from a region where no such formation was expected. It sits outside the anticipated bounds of galactic density, showing gravitational strength without a corresponding display of mass. Unlike the Sloan or Hercules Corona Borealis walls, this formation doesn't appear to follow the architecture of the known cosmic web. It seems misaligned, even disconnected. It behaves as though it exists in parallel, adjacent to the structure of the observable universe but not integrated into it. One model suggests that it may be a massive extension of the dark matter web, an unseen superstructure that stretches between our observable zone and something farther, deeper, and altogether foreign. That's when the controversial theories began to surface. A growing number of physicists and cosmologists started proposing a possibility that previously only lived in the realm of speculative physics. What if this structure isn't part of our universe at all? This theory is built on the concept of a multiverse, where our universe is one bubble among many in a far grander cosmic foam. Each bubble could have its own laws of physics, its own matter, and its own dimensions of space and time. If such a universe were to drift close enough to ours, or if they once interacted during or before the Big Bang, a residual scar, some overlapping structure, might be left imprinted on our cosmic landscape. In other words, the structure detected might not be inside our universe. It might be pressing against it. Supporters of this theory point to the structure's location at the very edge of the observable universe. They argue that its gravitational pull is too smooth, too evenly distributed, to have evolved naturally under the same rules that formed our galaxies and clusters. They also highlight that no optical data shows any corresponding matter, no light, no X-rays, no emissions at all. If it is truly made of dark matter, then it's the largest isolated concentration ever found. But if it isn't, then it might be the result of something colliding with or interacting across the boundary of what we call reality. Skeptics warn against jumping to such dramatic conclusions. They argue the data, while extraordinary, is still incomplete. The structure's dimensions are based on indirect inference. The possibility of some unknown foreground interference, or a quirk in the modeling software, still exists. But even these critics admit that no current cosmological simulation predicts a structure of this magnitude in that location, and none can explain the gravitational symmetry it appears to possess. There's even a fringe view, one still whispered rather than published, that this might be a form of artificial construction. Not a cosmic wall or supercluster, but something else entirely. A Dyson-level megastructure. A simulation echo. These ideas, while far from the mainstream, are gaining traction online and in private physics forums. What is certain is this: the structure challenges the boundary between what is considered observable and what is imagined. It blurs the line between data and mystery. It forces us to reconsider what defines a structure in the first place. If it has no light, no matter, and no borders, but can still warp space itself, then perhaps our definitions are outdated. Perhaps the cosmos is not just stranger than we thought, but stranger than we are capable of thinking. This is not just a question of classification. It is a direct confrontation with the limits of our understanding. And as scientists continue to map the edges of this structure, what they find may reshape not only our models of the universe, but our concept of existence itself. When the data divides the scientific world, no discovery of this scale ever enters the world quietly. As soon as the research team released their initial findings, the shockwave rippled across the astrophysics community. The first formal paper appeared on a preprint server, a detailed breakdown of gravitational lensing irregularities and the surrounding mass distribution maps. Within hours, downloads surged into the thousands. Peer institutions, observatories, and university departments began poring over the data with forensic precision, seeking to understand what the team had actually found, or whether they had made a colossal mistake. The publication didn't go unnoticed by major journals. Within 2 weeks, the findings were submitted to the Astrophysical Journal and later reviewed by monthly notices of the Royal Astronomical Society. These weren't fringe venues, they were the heart of academic astrophysics. What surprised many was not just how fast the journals responded, but how divided the peer reviewers were. Some praised the methodology, citing the careful statistical analysis, multi-source data triangulation, and use of cross-survey confirmations. Others issued stern warnings about premature conclusions and the risk of sensationalism. One major critique came from a group at Caltech, who published a rebuttal suggesting that the observed gravitational lensing pattern could be explained by a dense foreground mass previously unaccounted for. They argued that a mischaracterization of intervening galactic dust or minor lensing from unresolved sources might have created a false signal. In other words, the structure wasn't real. It was an illusion crafted by overlapping effects. The original research team responded by releasing additional simulations and opening up their data to public scrutiny. They even challenged skeptics to submit competing models that could explain the lensing without invoking a massive, unseen structure. Over the next few months, debate intensified. Some astronomers, especially those working in observational cosmology, began reprocessing their own archival data in light of the claims. A few found weak but consistent lensing patterns in the same region, which added credibility. Others remained unconvinced, saying the evidence fell just short of meeting the burden of proof required for rewriting cosmological theory. As peer review continued, the controversy began to spill beyond scientific journals and into mainstream media. Headlines touted the possible discovery of something beyond the known universe. Science communicators and YouTubers latched onto the drama, and public fascination exploded. The story took on a life of its own, fueled by intrigue, mystery, and the allure of the unknown. The general public wasn't debating error margins or survey sensitivity. They were asking whether this meant we were looking at the edge of reality. That public enthusiasm brought pressure, and pressure brought more scrutiny. Several observatories were pushed to conduct independent scans of the region using different instruments. One group at the University of Tokyo attempted to replicate the gravitational lensing results using data from the Subaru telescope. Their results were inconclusive. They saw minor distortions, but not with the strength or clarity reported by the original team. Meanwhile, a group at the Harvard-Smithsonian Center for Astrophysics launched a high-profile statistical review, warning that the findings might suffer from what they called cosmic confirmation bias, where researchers, eager to find anomalies, inadvertently assign significance to noise. But support wasn't lacking either. The team at the European Southern Observatory produced a review affirming the presence of an unusual gravitational anomaly in the specified coordinates. A panel at the Kavli Institute for Cosmological Physics hosted a symposium, bringing together supporters and skeptics in the same room. The event, broadcast online, became one of the most watched science panels of the year. What stood out wasn't consensus, but the tone. Gone was the dismissal often seen in speculative science. In its place was something more cautious, an acknowledgement that while the evidence was incomplete, it wasn't easily dismissed. The debate eventually reached one of the most sensitive issues in modern astronomy, the reliability of the instruments themselves. Critics began questioning whether the telescopes used, particularly Euclid's gravitational lensing measurements and Vera Rubin's early data, were calibrated accurately enough to detect such a massive structure. They pointed to minute mechanical drift, cosmic ray interference, and even computational errors introduced during post-processing. Supporters countered that the data was independently verified across at least 3 systems and that dismissing it outright because of minor potential instrument flaws was disingenuous. Amid this technical tug-of-war, the question hanging over everyone's head was deceptively simple. If the data is accurate, what does it mean? Does this discovery rewrite our understanding of cosmic structure? Or does it expose the fragility of the instruments and models we've come to trust? As of now, the scientific community remains split. Some researchers have adopted a wait-and-see stance, urging more data before drawing conclusions. Others are already exploring what this structure could mean for cosmological constants, the shape of the universe, and the possible presence of regions beyond our observable horizon. No one, however, is ignoring it. What started as a deep sky anomaly has become a philosophical fault line within the field. It pits conservative empiricism against bold interpretation. It asks whether we are still in the age of mapping the universe, or if we've stumbled into something unmappable. For now, the debate continues. But every passing day brings more eyes to that quiet patch of southern sky, where light bends in ways that refuse to be ignored. Implications. Does this mean the universe is bigger than we thought? When one discovery shakes the foundations of reality, the discovery of a gigantic structure at the very edge of the observable universe does more than just challenge astronomy. It threatens to unravel the very framework we use to understand reality. For centuries, science has been expanding the borders of the known universe, pushing outward with every new telescope, every deeper field, every gravitational map. But what happens when we reach a point where our tools still work, but the rules stop making sense? This structure is not just big. It appears to sit somewhere beyond the traditional definition of where our universe ends. That leaves us with a daunting question: is the universe actually much bigger than we ever thought? Some cosmologists believe this discovery may be the first concrete indicator of a multiverse. This concept, long dismissed as theoretical fantasy, proposes that our universe is merely one of many. Picture a cosmic foam, with each bubble representing an individual universe. Each of these universes could have entirely different physical laws, different constants, different timelines. In this model, our universe is no longer the whole of existence. It's just a single room in an endless mansion. The gravitational distortion detected by astronomers could be the result of interaction with another one of these rooms. Maybe not a collision, but a brushing of boundaries. A gravitational nudge from a neighboring universe. That opens up the even stranger idea of a connected cosmic web, not just within our universe, but spanning multiple realities. If dark matter forms a structure that stretches beyond the limits of our observation, could it be linking us to somewhere else? The cosmic web as we understand it consists of vast filaments of dark matter connecting galaxies across millions of light years. What if that structure doesn't stop at the edge of our universe? What if it continues, bridging realms we can't see, or even understand? This isn't just science fiction anymore. Some string theorists and quantum cosmologists have started taking these possibilities seriously, arguing that the interconnectedness we see in physics at the smallest scales may extend to the largest ones, too. Alongside multiverse theories, another idea gaining attention is simulation theory. The idea that we may be living inside a programmed reality. At first glance, it sounds absurd. But consider this: the presence of an anomalous, seemingly unreachable structure that still affects our universe could resemble a rendered object at the edge of a simulation. In computing, simulations often use limited rendering fields. The environment outside the user's view isn't fully rendered until needed. If our reality is based on similar logic, then the discovery of an impossibly large, out-of-bounds structure might indicate a flaw or a boundary in the system. Something left in the code. Something not meant to be seen. Some physicists who entertain simulation theory point to the uncanny precision of physical constants and the strange mathematical symmetry found in the laws of nature. If these were programmed, rather than random, the presence of a structure like this could represent either a glitch, a test, or an encoded message. The idea may sound radical, but it's drawing more serious discussion than ever before, especially as quantum computing begins to mirror patterns we observe in the universe. Then there's the matter of time itself. Time dilation, as described by Einstein's theory of relativity, shows us that time can stretch or compress depending on gravitational influence and velocity. In extreme cases, it behaves in ways that border on the surreal. If this structure is as massive as the data suggests, then its gravitational field may be warping time in its vicinity. That opens up possibilities about parallel dimensions where time flows differently. If the structure spans beyond our universe, perhaps it also intersects timelines or realities that move out of sync with our own. Some theorists propose that time, as we understand it, could be one facet of a multi-dimensional system, where different timelines fold over one another, sometimes intersecting. The implications of this discovery are overwhelming because they extend far beyond astrophysics. They touch on metaphysics, philosophy, and even consciousness. If this structure is a gateway, a bridge, a scar, or a boundary, then what lies beyond it could be as significant as everything we know within. It forces us to ask whether the universe has edges not just in space, but in logic, perception, and understanding. The structure isn't just a new puzzle piece. It's a crack in the cosmic mirror. And through that crack, we are starting to glimpse a reality far bigger, far older, and far stranger than anything we've imagined. The universe, it seems, has been holding secrets. And now, it's beginning to show its hand. Historical precedents, other, impossible, discoveries. It's when the universe broke the rules before. This isn't the first time scientists have faced something in the cosmos that defies explanation. In fact, astronomy has a long history of being humbled by discoveries that seemed impossible at the time. The universe has a way of reminding us that our models are just that, models. And when new data arrives, even the most sacred theories must bend or break. One of the earliest cosmic anomalies that shook the field was the discovery of the Great Attractor. In the 1970s and 1980s, astronomers began noticing something strange. Our galaxy, the Milky Way, along with the entire Virgo supercluster, was moving through space at a high velocity. But it wasn't drifting randomly. It was being pulled. And not by anything visible. The gravitational force was immense, enough to redirect entire clusters of galaxies. Eventually, scientists traced the motion toward a region in the southern sky, behind the dense clouds of the Milky Way's own disk. What they found wasn't a single massive galaxy or black hole, but a dense region of space now known as the Great Attractor. Even today, its full contents remain obscured. But its effect is undeniable. Galaxies move toward it, as though dragged by an invisible rope. It was one of the first major clues that much of the universe's mass remains hidden from view. Then came the cold spot. Discovered in the early 2000s through data from the Wilkinson Microwave Anisotropy Probe, the cold spot is a vast region in the cosmic microwave background radiation that is significantly cooler than the surrounding areas. The cosmic microwave background, or CMB, is the afterglow of the Big Bang, an almost uniform bath of radiation that should be consistent across the sky. But this particular patch was different. Some believed it was the result of a statistical fluke. Others proposed more exotic explanations, including the possibility that it marked the location of a supervoid or even hinted at the collision of our universe with another bubble universe. If true, it would be the first piece of evidence for a multiverse, buried in the sky's oldest light. Another disruptive discovery came in the form of the El Gordo cluster. Nicknamed the Fat One, El Gordo is a massive galaxy cluster found around 7 billion light-years away. What shocked scientists wasn't just its size, though it's one of the most massive clusters ever found, but its age. It formed far earlier in the universe's timeline than any known model could justify. According to standard cosmology, structures that massive should take far more time to assemble. Yet there it was, sitting in the early universe like a cosmic contradiction. Its existence forced astrophysicists to rethink how quickly matter could clump together after the Big Bang. Similarly, the discovery of mature galaxies just a few hundred million years after the Big Bang by the James Webb Space Telescope continues to challenge assumptions. These galaxies are too large, too evolved, and too organized for their time. They suggest that either the universe formed structure faster than we thought, or that our understanding of the early cosmos is incomplete. These discoveries serve as a crucial reminder that science is not static. Every new finding must be tested, retested, and placed into the larger framework of understanding. But when something doesn't fit, it's not the data that gets dismissed, it's the theory that must evolve. This is how science advances. Theories are tools, not truths. And sometimes those tools need sharpening. Other times, they need replacing entirely. The discovery of the giant cosmic structure beyond the known universe may feel unprecedented, but it fits into a long tradition of the cosmos pushing back against our assumptions. It's another crack in the wall. Another whisper from the edge. And just like the Great Attractor, the Cold Spot, and El Gordo, it demands that we listen. Because when the universe speaks, it often says what we least expect to hear. Ancient myths and modern science collide. Echoes of the unknown from a forgotten past. Long before telescopes mapped the stars or equations hinted at dark matter, ancient civilizations spoke of realms beyond the sky. These stories, passed down through generations, were woven into the spiritual and cosmological beliefs of nearly every culture. While modern science tends to view them as metaphorical, recent discoveries, like the massive structure found beyond the known universe, force us to reconsider whether some ancient myths might have been more than just symbolic imagination. In Hindu cosmology, the universe is cyclical and layered, composed of multiple realms known as lokas. Some of these lokas exist in the heavens, while others stretch into realms of darkness and beyond. The Rig Veda, one of the oldest known texts, describes a cosmic order sustained by invisible forces. It speaks of worlds beyond our perception, hidden behind veils of illusion, where creation and destruction occur in cycles spanning billions of years. That timeline, once dismissed as mystical exaggeration, now aligns strangely. Norse mythology offers a different yet equally provocative perspective. The Norse universe is structured around Yggdrasil, the world tree, connecting 9 distinct realms. These include Asgard, Midgard, and the mysterious Nilheim, a dark, cold region considered unreachable. The very idea of a structured multiverse, connected by invisible threads and governed by unseen laws, parallels the notion of a cosmic web and even the possibility of alternate realities. The myths often describe these realms as being layered or adjacent, existing simultaneously but requiring special conditions to perceive or enter. Today, physicists speak of parallel dimensions and unseen forces with an eerily similar cadence. Ancient Egyptian cosmology introduces yet another layer. The Duat, their underworld, was more than just a land of the dead. It was a complex, multi-zoned realm that existed beyond the stars and was navigated by both gods and souls. The Duat was said to be invisible to the living, yet constantly influencing the material world. It was filled with obstacles, cosmic entities, and a river that bore resemblance to the Milky Way. Some scholars now suggest that the Egyptians may have been observing celestial patterns and encoding them in spiritual metaphor. When juxtaposed with modern science, these narratives start to feel less like primitive guesses and more like distant echoes. Perhaps ancient people, using a different language and worldview, were attempting to describe phenomena we're only now beginning to detect, forces beyond sight, realms beyond comprehension, and structures so large they escape ordinary perception. It's tempting to dismiss mythology as fiction. Yet myth has always been humanity's first attempt at explaining the unexplained. Before there were models and telescopes, there were metaphors. And sometimes, metaphor carries fragments of truth. As science continues to reveal a universe more layered and interconnected than we ever imagined, the old stories begin to shimmer with renewed relevance. Maybe those ancient voices weren't wrong. Maybe they were just speaking in a language we're only now beginning to understand. The deeper we peer into the cosmos, the more we may find that the line between science and myth is not a boundary, but a bridge. The next steps in the search, turning the unknown into a roadmap. Now that the existence of this gigantic structure has been acknowledged, the scientific community has entered the next phase, confirmation and exploration. This is the point in every great discovery where initial surprise must give way to methodical investigation. The goal is not just to prove the structure is real, but to understand what it is, how it formed, and what it could tell us about the universe at large. The data that initially hinted at its existence came from multiple sources, but now researchers are working to coordinate targeted telescope scans focused specifically on that region of space. Gravitational lensing remains the most powerful tool in the arsenal. Scientists are developing refined algorithms to isolate distortions in light more clearly and eliminate any interference from foreground objects. Rather than relying on a single survey or telescope, astronomers are cross-referencing gravitational data with cosmic microwave background readings, galaxy redshift surveys, and motion patterns of nearby cosmic structures. The idea is to triangulate the structure's presence using as many independent data streams as possible. Each layer of confirmation adds strength to the case and reduces the margin for error. To support this effort, some of the world's most advanced observational instruments are being directed toward the coordinates where the anomaly was first detected. The James Webb Space Telescope, although primarily focused on early galaxy formation, is now being used in part to gather ultra-deep field images of the region. While Webb cannot see dark matter directly, it can detect the formation patterns of galaxies and stars that might be influenced by an unseen gravitational force. Looking ahead, one of the most anticipated contributions is expected from the upcoming Nancy Grace Roman Space Telescope. Scheduled to launch within the next few years, this observatory is designed specifically to study dark energy and dark matter by capturing wide-field images of space at extraordinary resolution. It will survey more than 100 times the area of sky that the Hubble Space Telescope could at once. Scientists believe its ability to map dark matter with precision through weak gravitational lensing will provide the clearest picture yet of this mysterious structure's scale and shape. On Earth, the Vera Rubin Observatory continues its work through the legacy survey of space and time. The Rubin team is updating their imaging protocols to increase sensitivity in the southern sky where the structure is located. The LSST is expected to capture 30 terabytes of data each night, creating a rolling, dynamic model of the cosmos that allows for real-time anomaly detection. If the structure shifts, changes, or influences nearby galaxy clusters, the Rubin Observatory is likely to detect it. But the search is no longer limited to institutions and governments. With so much public data being released in real time, a growing number of citizen scientists are now joining the hunt. Platforms like Zooniverse and CosmoQuest are opening portals for amateur astronomers and data enthusiasts to analyze telescope images, flag unusual patterns, and contribute to ongoing surveys. Some of the most valuable insights in recent years have come from the crowd, unexpected discoveries made not by professionals, but by passionate observers with a trained eye for the extraordinary. This collaboration between professionals and the public represents a new frontier in science. The cosmos is vast, and so is the ocean of data we now collect daily. Processing that information requires not only machines and algorithms, but human curiosity and attention. The search for the structure beyond the known universe has become a global effort. It is no longer confined to a single lab or paper, it is a shared question posed to the entire world. In this new chapter, science is doing what it does best. It's asking better questions. It's building better instruments. And it's inviting everyone to look a little deeper into the dark. Because what we find next may change everything again. And this time, the world will be watching. Speculative theories gaining momentum when the impossible demands a theory. With the weight of observational data pointing to the existence of something massive and previously undetected, theoretical physicists have begun stepping beyond traditional models to explain what might be going on. While the majority of the astrophysics community remains grounded in careful data analysis, a growing faction is exploring the possibility that the structure recently detected might not fit within the established boundaries of Big Bang cosmology. These are not wild guesses made in isolation but informed speculations that attempt to reconcile the data with physics at the bleeding edge of understanding. One of the most talked about theories centers on the idea of a leak at the edge of the universe. If our observable universe is one bubble in a much larger multiverse, then perhaps the gravitational distortion we are detecting is coming from beyond our local spacetime. In this view, the structure is not within our universe, but pressing against it. It might be part of another universe with different laws of physics, or even a kind of gravitational echo from a previous cosmic cycle. A leak wouldn't necessarily mean a rupture in space, but rather a kind of bleeding of gravitational force from a neighboring dimension or bubble universe into our own. It would be a subtle but undeniable influence, one that hints at boundaries we never expected to measure. Another theory suggests that we may be witnessing the influence of an external gravitational force unlike anything previously modeled. Our cosmic web, the vast network of dark matter and galaxies that stretches across the universe, has always been considered internally consistent. Galaxies move and cluster based on known gravitational relationships. But if this newly discovered structure is affecting galaxy motion at large scales, and if it lies beyond our horizon, it could suggest that our universe is being subtly pulled by forces outside our visible domain. This kind of external tug could warp the cosmic web itself, creating strange filaments or stretching known structures in ways that can't be explained through internal mechanics alone. The most radical theory, and one gaining quiet momentum, is that the structure simply shouldn't exist if the standard Big Bang model is correct. According to the timeline of cosmic evolution, there should not have been enough time for a structure of this magnitude and uniformity to form naturally. It breaks the assumed speed limits of gravity and structure formation. That means one of two things must be true. Either our timeline of the early universe is wrong, or the physical laws that govern large-scale structure formation are incomplete. Both possibilities are equally disruptive to modern cosmology. These ideas remain speculative for now, but they have begun to shape the questions being asked in research institutions and cosmology departments around the world. The boundary between accepted theory and open mystery is thinner than ever. And as more data emerges, the possibility that we are looking at a phenomenon beyond anything Big Bang cosmology has accounted for becomes harder to ignore. What was once labeled impossible is now being modeled, simulated, and tested, because the universe doesn't care what we think is supposed to exist. It only reveals what already does. What if it's not natural? The uncomfortable possibility of intelligence, when faced with something so massive, so perfectly symmetrical, and so far beyond the scope of current cosmology, a few bold voices have begun to ask the question no one wants to ask first. What if the structure isn't natural at all? It's a possibility that many scientists consider taboo, not because it lacks intrigue, but because it stretches the boundary between science and speculation. Yet as the gravitational data continues to defy natural explanations, the whispers have grown louder. Could we be witnessing a feat of engineering so vast it redefines the limits of possibility? The most talked about concept among these speculative theories is the idea of a Dyson swarm. A Dyson swarm is a hypothetical megastructure that encircles a star, or even a series of stars, to harvest energy. While originally envisioned to surround a single solar system, some theorists have taken the idea further, imagining structures that operate on galactic or intergalactic scales. If an advanced civilization, millions or even billions of years older than ours, had the time and resources, it might attempt such a feat. The structure we've detected shows no light signature, no radio emissions, and no thermal radiation. But that could mean it's deliberately cloaked or built with materials beyond our understanding. A swarm that manipulates gravity or dark matter itself would leave no visible trace, only the kind of gravitational distortions now puzzling astronomers. This brings us to the idea of a Kardashev Type 3 civilization. The Kardashev scale measures a civilization's level of technological advancement based on energy consumption. Type 1 uses all the energy of its home planet. Type 2 harnesses the energy of its star. Type 3 would be capable of controlling the energy output of an entire galaxy. To us, that level of advancement feels inconceivable. But from a cosmic timeline perspective, we are relative infants. The universe is nearly 14 billion years old. Civilizations with a head start of even a few million years could be operating with technologies we would interpret as natural phenomena simply because we have no framework to recognize them as artificial. Some physicists caution that invoking intelligent design veers too close to science fiction or, worse, pseudoscience. Yet the intelligent design discussed here is not religious or spiritual in nature. It refers to the possibility that highly advanced entities, biological or artificial, may have had a hand in shaping parts of the universe. Some theoretical models even suggest that the fine-tuning of physical constants and the strange mathematical elegance of the cosmos point not to chance, but to deliberate calibration. If this is true, then a massive structure beyond our known universe might not be an anomaly. It could be a marker, a tool, a boundary set not by physics, but by intention. The idea remains speculative. No one claims certainty. But as data accumulates and explanations fall short, the possibility that intelligence, whether alien or ancient, plays a role in what we're seeing is no longer something that can be dismissed outright. The cosmos may be alive not just in movement, but in mind. And that is a possibility we are only beginning to confront. What this means for us on Earth, between insignificance and connection. As telescopes peer deeper into the cosmos and data reveals structures beyond comprehension, we are left with a question that no instrument can measure. What does this discovery mean for us, here on Earth? A gigantic, invisible structure beyond the known universe may seem too distant to affect daily life. Yet its implications ripple through everything, from our sense of purpose to our understanding of reality. It forces us to confront both the terrifying vastness of the universe and the possibility that we may not be as alone or as irrelevant as we thought. On one hand, the realization that our entire galaxy is just a dot within a filament, which is itself part of a larger web, and that even this vast architecture may be influenced by something even larger, can provoke a sense of cosmic insignificance. The idea that Earth is just a speck, orbiting a modest star on the edge of an average galaxy, has been humbling for centuries. This new discovery deepens that humility. If structures exist beyond the limits of light and time, we are truly just beginning to scratch the surface of what reality is. Our maps are incomplete. Our theories are temporary scaffolds. Our position in the universe may be even smaller than we imagined. Yet paradoxically, this same discovery opens a door to a deeper sense of connection. The fact that we, fragile and finite beings, can build machines capable of detecting the gravitational fingerprint of a structure that may lie beyond the visible universe is nothing short of extraordinary. It means that consciousness, emerging from stardust on one small planet, is capable of reaching across billions of light years to ask the most profound questions. It suggests that understanding is not limited by size or position. There is meaning in the fact that we can measure, question, and wonder. The psychological impact of such a discovery is hard to quantify. For some, it may provoke awe and curiosity. For others, anxiety or existential dread. But whether it leads to spiritual reflection or scientific ambition, it demands that we expand our minds to fit a universe that refuses to be small. It challenges traditional belief systems, encourages philosophical reconsideration, and invites spiritual perspectives not necessarily bound to religion, but rooted in reverence for the unknown. If the universe is far larger than what we can see, if it contains forces, patterns, or intelligences beyond our comprehension, then our role as observers gains new weight. We are not the center of the universe, but we are not disconnected from it either. We are part of its story. Perhaps even essential to it. This structure, whatever it turns out to be, is more than a scientific anomaly. It is a mirror reflecting our deepest questions back at us. It asks who we are in a universe so vast. It asks whether we are truly insignificant, or uniquely aware of the mystery that surrounds us. The answer may be both. And that is what makes it matter. Has something like this been seen before? Clues we missed in the shadow. As scientists piece together this monumental discovery, some have started looking backward, combing through decades of archival data with fresh eyes. And what they're finding is unsettling. It turns out this might not be the first time the universe tried to show us something was there. In fact, the earliest whispers of this structure may date back over 30 years, to the 1990s, hidden in the static of old satellite transmissions and forgotten gravitational anomalies. Early cosmological satellites like COBE and even high-altitude balloon missions recorded faint distortions in the same region now under scrutiny. At the time, the deviations were small, inconsistent, and easily dismissed as noise. Data compression algorithms, limited resolution, and lack of corroborating observations meant the signals were categorized as errors or random fluctuations. But now, when those same patches are reprocessed using modern algorithms, patterns begin to emerge: weak gravitational arcs, unexplained redshift shifts, and anomalies in microwave background temperature gradients. Some of these discrepancies appeared again in early Planck data but were dismissed during calibration. Scientists were hunting for more conventional signatures. No one expected a gravitational footprint from a structure potentially beyond the universe itself. The signs were there, but the frameworks to interpret them weren't. So now we ask, were we warned? Was the cosmos whispering about this hidden giant all along, and we simply didn't know how to listen? With new tools and fresh perspectives, the veil may continue to lift. And if a structure like this has already shocked us once, what else might be waiting? What if the next edge we discover isn't the end of the universe, but another beginning? The deeper we look, the louder the unknown calls.